Hi guys, how are you? I hope you are doing well. Today we're gonna continue with chapter 14. We're gonna talk about, after partial derivatives, today we're gonna talk about the chain rule and directional derivatives. So let's first start with the chain rule. And let me remind you the case of function of single variable. So if you have, let's say, y, function of x, so y is equal f of x, so just a single variable, right? And then let's suppose that x is also a function of t. So x is equal to x of t, right? So then y, of course, y would be, so f of x, but x is x of t. So that's f of x of t, right? So then y is actually a function of t, right? And so the question is, what's y prime of t? Well, y prime of t, so we're gonna apply the chain rule because to find y prime of t, because you see y is a composition of two functions. So you have f and then you have x. Okay, so f, function f composed with the function x, right? So composition of two functions. So then y prime of t, which is dy dt. Well, first we have f, right? So we need derivative of f with respect to x. So df dx, so df dx times, and then you have this function x of t, so it's dx dt times dx dt. Okay, so again, what I am saying is that, so y, which is f of x, okay, so y is a function of x, and x itself is a function of t, right? So if you want to compute the derivative of y with respect to t, okay, so then you have to multiply derivative here, function f with respect to x, so dy dx times dx dt, okay? So now we're going to extend this chain rule to several variables. So let's extend it to several variables. Okay. So now let's say we have a function f of two variables, x, y, not just a single variable, but two variables, x and y. So that will be z. So z is equal to f of x, y. And let's say x is a function of t, so x is x of t. And y is also a function of t, so y is equal to y of t. Okay, so in other words, this z would be f of x of t, y of t. Okay, so z is actually function of t. Okay, so now the question, so what's z prime of t? So what's dz dt? What's the derivative of z with respect to t? Well, so this is a chain rule. So then actually derivative of z with respect to t would be equal to, so basically guys, what I'm saying here, you have this, so you have this function z here, it's a function of x and y, right? And x itself is a function of t, and y is a function of t, right? So then if you want to compute the derivative of z with respect to t, so we want to compute the derivative of z with respect to t. So there are two different ways, to go, like in this tree here, there are two different ways to go from z to t, right? So we're going to go through x, or we can go through y. So if you go through x, then that will be derivative of z with respect to x. So it's dz, or partial derivative of z with respect to x, because z is a function of two variables. So it's partial z, partial x, and then x t, so times dx dt. So that will be the first way. So what I am saying is, if you go through this way, so first it's partial z, partial x times dx dt. Now, plus, now we're going to go through the other second way. So you can go through y, so that will be partial z, partial y, times partial y, partial t, or derivative of y with respect to t. So plus here, partial z, partial y, dy dt. Okay, so that would be the chain rule. So if you have here, again, you have function z. So z is a function of x, y. X is a function of single variable, so x is x of t. And y, so here x is a function of t, and y is also a function of t. Okay, so both are a function of single variable. Let's do an example here. Example. So let's say a function as z is equal, so f of x, y is equal x times y squared. Okay, it's a function of two variables. And now let's say x of t is equal to, let's say, t squared plus 1. Okay, and y, which is a function of t, y of t, is equal to, let's say, just the exponential of t. Okay. So then here, what I am saying is, then z, of course, z would be a function, so f of xt, y of t. So z is actually a function of t. Okay, so if you replace x by t squared plus 1 and y by e exponential of t, so then z would be, so here what I'm saying is z would be equal to, it's x y squared, but then z of t, so this is z of xy, right? Now z of t, so x is equal to t squared plus 1 times y squared. Y is e to the t, right? So e to the t squared. So now z is a function of just a single variable, which is t, right? So here, this is z of t. Okay, this is z of xy, and this is z of t. Now let's compute derivative of z with respect to t. So z prime of t, so z prime of t, which is dz dt. So if you apply the chain rule, so we said if you use the chain rule, that will be equal to what? So by the chain rule, that will be equal to first partial z partial x times dx dt. So partial z, let me just write down the formula. So partial z partial x dx dt plus partial z partial y dy dt. So what's partial z partial x? So this is my z, right? So partial z partial x here, so partial z partial x, so we derive with respect to x, so then y is a constant. So this is like x times, so y is a constant, so of course y squared is also constant, so that's like x times a constant. And what's the derivative of x times a constant? Like what's the derivative of 3x? That would be just 3, right? Or you can also apply the product rule. So if you apply the product rule, so the derivative of x is 1 times y squared, okay, plus, and then derivative of, so x times derivative of y squared, but y is a constant, so the y squared is a constant, so that's just 0, so x times 0. So partial z partial x is just y squared. So this partial z partial x is y squared. Now, times dx dt. So what's the derivative of x with respect to t? X is t squared plus 1. So derivative of x with respect to t is 2t. So here it's times 2t. Okay, plus, now what's partial z partial y? So what's partial z partial y? So let's see. Here, partial z partial y, so we consider x as a constant, so that will be equal, so apply the product rule because here it's a multiplication, x times y squared, product rule, so derivative of x is a constant, so this will be 0 times y squared plus x times derivative of y squared, which is 2y. So here again, x is a constant, y is a variable. Derivative of y squared will be 2y. So that's x times 2y, so that's 2xy. So here derivative of z with respect to y, that will be 2xy. Plus, times, right, dy dt, so derivative of y with respect to t. So what will be derivative of y with respect to t? Well, y is e to the t, so derivative of e to the t with respect to t is just e to the t. So that's dy dt would be just e to the t. Okay, so what I'm saying here is that dz dt, or z prime of t, so z prime of t is equal to y squared times 2t plus 2xy times exponential of t. But we can just replace here, so we know y squared is, so again, this is z prime of t. So y is equal to e to the t, right? So y squared, that's e to the t squared times 2t plus 2 times x. So what's x in terms of t? X is t squared plus 1. So 2 times t squared plus 1 times y. What's y? Y is e to the t, so times e to the t. And then times another e to the t. Okay. So that's my z prime of t. So in other words, that will be equal to, so then z prime of t is e to the, so that's 2t times 2t plus 2 times t squared plus 1 e to the t plus times e to the t, so that will be equal to e to the 2t. Okay, so that's a z prime of t. Okay, now guys, well, we can have more fun, and instead of, let's say, two variables, let's say we have three variables. So let's say, for example, you have z is equal to function of, so it's a function of, let's say, three variables, u, v, w. Okay, now each of these functions u, v, w are functions not just of single variable, but let's say it's they are functions of two variables. So let's say u is a function of s and t. V is a function of s and t, and w is also a function of s and t. Okay. So z is a function of three variables, but each function here, each variable is a function of two variables. So then, if you replace u by u of s of t, v by v of s of t, so z would be a function of s and t, right? So z, this is z of s of t, would be f of u of s of t, v of s of t, w of s of t. Okay, so now z, it's a function of s and t, because u is a function of s and t, which means that you can just replace u by in terms of s and t. You can also replace v by in terms of s and t, and the same for w. Okay, so you can just replace everything in terms of s and t. So you end up with a function of s and t. So now the question: what's the derivative of z? So what would be the derivative of the? So here, z is a function of two variables, right? So what's the derivative of z with respect to s? And what will be the derivative of the z with respect to, so we said two variables, right? S and t. So what's the derivative of z with respect to t? Okay, so let's draw this tree here. So we have, z. First, we said that z is a function of three variables. So you have u here, and then you have v, and then w, right? Now, u itself is a function of s and t. So u here is a function of s and t, v is a function of s and t, w is a function of s and t, right? So let's say you want to compute partial z, partial s, okay? So there are three ways to go from z to s. So first you can go through u, right? So that will be partial z, partial u, and then partial u partial s, or you can go through v. So that would be like partial z, partial v, and then partial v, partial s. Or you can go through w here, so that's partial z, partial w, and then partial w, partial s, right? So each time, so you want to derive z with respect to x, so you can go to go from z to s. There are three different ways. You can go through u, or you can go through v, or you can go through w. Okay, so if you go through u, that means so that will be partial z, partial u, partial u, partial s, plus, then you go through v, right? So that will be partial z, partial v, partial v, partial s, and you can also go through w, so that's partial z, partial w, partial w, partial s. Okay, now for partial z, partial t, so again, you want to go from z to t, right? And again, there are three different ways to go from z to t. So you can go through u. So that's partial z, partial u, and then partial u, partial t. You can go through, from z to t, you can go through v. So that's partial z, partial v, partial v, partial t. And then finally through w. So that will be partial z, w, and then w, partial t. So that, if you go through u, so that's partial z, partial u, partial u, partial t. You can go through v, so that's partial z, partial v, partial v, partial t. Or finally, you can go through w, so it's partial z, partial w, partial w, partial t. Okay. Okay, so let's just do an example so you can see how to apply the formula. Example, so let's say z is equal to, so z is a function of u, v, w, and let's say just z is u squared plus v times w, okay? And let's say u is a function of s and t, so u s of t, so let's say u is s plus t, let's say v is s times t, and w, let's say it's s times e to the t. Okay. Now, let's say you want to compute partial z, partial t. Okay. So we want to go from z to t, right? So there are three different ways to go from z to t. So through u, through v, and through w. So if you go through u, that would be partial z, partial u, partial u, partial t. You can go through v, so that's partial z, partial v, partial v, partial t. And finally through w, partial z, partial w, partial w, partial t. Okay. So that will be equal to, so what's partial z, partial u? So you derive with respect to u. So it's u squared, derivative of u squared, that will be 2u plus v times w. So you derive with respect to u, which means that v and w are constant. So v times w would be also a constant. So and derivative of constant, of course, is 0. So that's just tu, okay? So that's partial z, partial u. It's equal to 2 times u. Now, what's partial u, partial t? Derivative of u with respect to t. So s would be a constant. Derivative of constant is 0. So that's 0 plus derivative of t. That's 1. So that's equal to, so 2 times 2u here times 1. So here we have 1 here. Okay. Plus. Now, partial z, partial v. So you derive with respect to v, so then u and w are constant. So first you have u squared. U squared, u is a constant, so u squared is a constant, derivative of constant is 0, plus, and then you can apply a product rule here. Derivative of v, it's 1, so what 1 times w plus v times derivative of w, but w is constant, so that's 0. So derivative of z with respect to v would be just 1 times w, so that's w here, times partial v, partial t, derivative of v with respect to t. So s is a constant, so that's here v is s times t. So apply product rule, s is a constant, derivative of constant is 0, so that's 0 times t plus s times derivative of t, which is 1. So that's times s plus, and then partial z, partial w. So then u and v are constant, derivative of u squared. U is a constant, derivative of u squared. U squared would be a constant too. So derivative of constant is 0, so the 0 plus v is a constant, v times w, so we apply a product rule. So derivative of v, that would be, v is a constant, so that's 0, 0 times w, plus v times derivative of w is 1. So it's 1 here times partial w, partial t. So here s times exponential of t, so that's a product rule as a constant, so product rule as a constant, derivative of constant is 0, so that's 0 times e to the t plus s times derivative of e to the t, which is e to the t, so that's s times e to the t. So then partial z, partial t would be equal to 2u plus w times s plus s e to the t. Now 2 times u, what's u? U is s plus t, right? U is s plus t, so we can brace here. So that's 2 times s plus t plus w. So w is s e to the t, so s e to the t times s, right? So s e to the t times s plus s e to the t, so plus s e to the t. Okay, and that will be, so 2 times s plus t plus s squared e to the t plus s e to the t. So that's partial z, partial t. Okay, so that's the derivative of the z with respect to t. Okay, guys, of course you can have more than 3 variables. You can have 4, 5, 6 variables, etc. You can find the general formula in the lecture notes with the examples. Anyway, so now let's move, before the directional derivative, let me just say a couple of words about the implicit differentiation. So the implicit differentiation. Okay, so let me explain this. Let me start with an example. So, for example, when you say, let's say you have y minus x squared equal to 0, right? So we have some equation here equal to 0. So y is equal to x minus x squared equal to 0 means that you can solve for y, right? Solve for y. So then y is equal to x squared, right? So y, which is a function of x, is equal to x squared, right? So here, the function y, so y is a function of x, and we can, we have an explicit expression of y. So we can solve explicitly for y here. So we have y is explicitly given it's equal to y is equal to x squared, right? So you know that the function y, which is a function of x, is equal to x squared. Now, let's say you have the following equation. Let's say you have x y squared minus x sine of y, okay, minus y e to the x equal to 0, okay? And again, y here is a function of x. So this is very important. So y is a function of x. Y is a function of x, okay? Now, the question is, can we solve for y here? Can we solve for y here? Okay. Well, the answer is no. We cannot solve, okay? It's impossible here to solve explicitly for y. So it's impossible here. So impossible. Okay, to solve for y. So which means we don't have an explicit expression of y, right? We don't know what's the expression of the exact expression of y, right? So we don't have the explicit expression of y, okay? However, we have this relation between x and y, right? We know that y and x, y being a function of x, so y and x, they satisfy this equation here. But the problem is, again, is that we cannot solve for y. So we don't know exactly what's the exact expression of y, okay? So we say in this case that y is implicitly defined by this equation here. Now the problem is you want to, y is a function of x, right, in both cases. So you want to compute y prime. So here, of course, y is x squared, so y prime, of course, would be just 2x, right? You know what's the derivative of y here, it's very easy, right? But then the question, what would be the, so the question here, what would be the derivative of, what would be y prime of x? What would be the derivative of y with respect to x, okay? Again, the thing is, you don't know exactly you don't know the explicit expression of y. So here, in this case, in the second case, we say that y is implicitly defined by, the equation by x y squared minus x sine of y minus y e to the x. Okay, so y, which is a function of x, is implicitly defined by this equation. We cannot solve for y, so we don't know what's the exact expression of y. However, we want to find y prime of x. Okay, well, so we do have a formula for that. So let's say, so the formula is the following. So let's say you have a function f of x and y, which is itself a function of x. Okay, so f is a function of x and y is itself is a function of x. And you want to compute y prime of x. Then you see here f is equal to 0. So derivative of f is 0. So if you apply the chain rule here, actually, you know that partial f, partial x. So here, I mean, the variable is x. So partial f, partial x, dx is 1, plus partial f, partial y, okay, dy dx, that's equal to 0 because a function f is equal to 0, okay? So then you can, here again, this partial f, partial x here is supposed to have dx because the variable is x here, right? So dx, this is equal to 1. Of course, this is just 1 here, okay? So then the formula is the following. So dy dx, y prime of x, y prime of x, so then dy dx would be equal to, so you solve for dy dx, so that's minus partial f, partial x, over partial f, partial y. Okay, so that's the formula for y prime of x using the chain rule. Okay, so for example, let's do an example so you can see what I'm talking about here. So example, let's say you have x y squared minus x sine of y equal to 0. Okay, and here y is a function of x, so y is equal to y of x, right? Y is a function of x. Well, you want to compute y prime of x, right? You want to compute y prime of x, the dy dx. However, again, you cannot solve here. We cannot solve for y, so we don't have an explicit expression of y, so we cannot really just explicitly compute y prime of x. So we're gonna use the chain rule. So we said dy dx is supposed to be, so what's my function f here? You see here you have a function f equal, you have this function f here equal to 0, right? That's my function f. So here, this thing here is equal to 0, so that's my function f. So that's f of xy. Okay, that's my function f. And so the formula says it's minus partial f, partial x over partial f, partial y. So then y prime of x. So what's minus? What's partial f partial x? Derivative of f with respect to x. So we consider y as a constant. All right. So y is a constant. So derivative of x y squared. Y squared is constant. So it's just minus. So here. So derivative. You can use the product rule if you want. Okay. Y is a constant. So it's derivative of x would be 1 times y squared plus x times derivative of a constant, which is 0. So it's just equal to y squared here minus, and then the same here, this y is a constant, so sine of y is a constant, so x times sine of y. So the derivative with respect to x would be just sine of y. That's a constant here over partial f partial x. Now we consider here it's partial f partial y here. This is partial f here, partial y. So now we consider x as a constant. So derivative of xy squared, x is a constant. So that will be 2xy minus derivative of x times sine of y. X is a constant, so 0, we use the product rule, so x is a constant, 0 times sine of y plus x times the derivative of sine of y. The derivative of sine is cosine, so that's x times cosine of y. So it's 2xy here minus x cosine of y. Okay, so that's the derivative. So this is the answer here. That's y prime of x. So you can compute y prime of x in terms of x and y, of course, right? And so that would be the answer. So the y prime of x is equal to this minus y squared minus sine of y over 2xy minus x cosine of y. Okay. Well, you can have more than 2 variables. Let's say you have 3 variables. So now let's say you have f of x, y, z equal to 0. Okay. And z, you know that z is a function of x and y. Okay. So here, basically what I'm saying is that you have only 2 independent variables, x and y, and the variable z is actually depends on x and y. So z is a function of x and y. Okay, so before here we have f of x y, but only x. So only y is a function of x. So y is a function of x. Here I am saying you have x, y, z, but then z is a function of x and y. Okay, then of course. Here you want to compute the derivative of the z with respect to x and the derivative of z with respect to y. So then partial z partial x would be minus partial f partial x over partial f partial z, and partial z partial y would be minus partial f partial y over partial f partial z. Okay, again, using the idea is to use the chain rule. You can just use the chain rule. Okay, so let's have an example. Okay, so you have a function z of 2 variables. Okay, and then let's say the function z satisfies x squared z plus y e to the, let's say y e to the xz, okay, equal to 0. Okay, so here it's not, we cannot really solve for z, okay, but you cannot solve for z, we cannot solve for z. So we don't know the explicit expression of z in terms of x and y. So z is implicitly defined by these equations because we cannot have an explicit expression of z. However, we can compute, let's say, a partial z So what would be partial z partial y, for example? So we said it's minus, so the formula is the following. It's minus partial z partial y, it's minus partial f partial y over partial f partial z. So it's minus partial f partial y over partial f partial z. So what's capital F here? What's the function f here? It's just this equation here. So capital F, this is my capital F of x, y, z. So let's compute this. What's partial f partial y? So it's equal to minus partial f partial y. So x and z are constant, right? So here, this x here and this z here are constant. Derivative of constant is 0. So the derivative of this whole thing is just 0. Now, y times e to the xz. So x and z again are constant. So this thing here is a constant. So here we have a product. So it's y times a constant. So derivative of y is 1 times the constant. So 1 times the constant plus, y times derivative of constant is 0. So it's just 1 times e to the xz over. Now what's partial f partial z? So partial f partial z, x and y are constant. So this x here is a constant. Here it's a product. So derivative of constant is 0. So derivative of x squared is 0 times z plus x squared times derivative of z. It's 1. So here it's x squared plus, then here same. So y is a constant, derivative of constant is 0. So that's a 0 times applied product rule. So this is a 0 times e. So it's a 0 plus y times. So now what's the derivative of e to the xz? Okay, so derivative of e to the xz, this is, well, it's supposed to be a chain rule here. So we are using, remember guys, if you have e to the f of x, so the derivative would be f prime e to the f, okay? So e to the xz, x is a constant. You can just think of x as a constant. So derivative with respect to z, so that will be derivative of this function here. Derivative of this function with respect to z, x is a constant. So that would be x times e to the f, e to the same function, so e to the xz. Okay, so then partial z, partial y is actually minus e to the xz over x squared plus y x e to the xz. Okay, so that's the final answer. Okay, guys. So now, so that's for the implicit differentiation. Now let's move to the directional derivative. Okay. So let's say you have now you have a function of two variables. So z is equal to f of xy. Okay, so this is my x-axis, this is my y-axis, and this is here, this is the z-axis. Okay, and you have the graph of f. So let's say this is here, this is f of xy. So here, this is f of xy here. Okay, and let's take a point. So let's take a point x0, y0. So this is this point. Okay, so this is x0, y0. So let me just remind you here, if you want to compute a partial f, let's say partial x in the partial f, partial x. So let's say you want to compute partial f, partial x at the point x0, y0. Okay. So let me just remind you the interpretation of this partial f partial x. So we said here partial f partial x means that y is a constant, so we fix y. So here your y is equal to y0. So we fix this line here. Here, let's say this is y equal to y0 here. So I have this line here, okay? And what you do, you take the image of this line by the function f, so there will be some, so first here, this is the image of my point, and you take, you know, the image of this line here by the function f, so it's gonna be some curve which lies on the graph of f of xy, or on the surface f of xy, okay? So that's the image here. And so we said this partial f partial x at x0, y0, it's just the rate of the slope, or let's say the slope of the tangent line, you know, to this curve at this point here, right? You have this point here. Okay, so then so you have this curve, so you have the tangent line to this curve at this point, right? And the partial f partial x at x0, y0 would be the slope of this tangent line to this curve, to this green curve here, okay? Which is the image of the line y equal to y0, the image of this line here. But let me just say here, this line here, you know, this line has a direction vector. So here the direction vector of this line, let's say a direction vector of this line would be the vector 1, 0, right? So this is just the line, I mean the x-axis. So that's the direction vector of this green line here. It's 1, 0. Now, if so this is, so here we're taking the vector, direction vector here, it's the vector 1, 0. Now, for partial f partial y at the point x0, y0, so here x is a constant, so x is fixed. So x is equal to, you know, so x here, this is my x equal to x0. So you have this line here, right? And the image of this line would be some curve here. So it would be some curve here. Let's say this curve would be this curve here. This one here, okay? And the tangent line to this curve here at the point, at the red point, at this point here, this one here. So let's say the tangent curve is this one. Let's take a black color here. So let's say here's the tangent line to this curve here. Then partial f partial y at x0, y0 would be the slope of this red black line here, okay? That's the tangent line to this curve here. But here, this curve, so this curve here is just the image of this line, right? The line x equal to x0. And what would be the direction vector of this line x equal to x0? So direction vector would be, it's just the y-axis. So the direction vector would be just the vector, let's say 0, 1. Okay. So here, this slope here, it's this slope, this tangent line here, it's actually associated to the vector 0, 1. Okay. Now, what I can do is, so let me just graph again because it's going to be too much otherwise. So let's see, here's my f. So what I'm saying is, so this is my x here. This is my x, this is my y, this is my z, this is my function f. We are saying you have a point here. So what I'm saying, if you take this 1, 0, then so this is the image here. This is my image. So if you take this vector here 1, 0, so you take the image of this curve, so there will be this line here, okay, and partial f, partial x would be tangent. Partial f, partial x would be the slope of this tangent line to this curve. Now I can take the vector 0, 1. Here's 0, 1. Okay, so you take this line here again, so it will be different line, a different curve here, right? So then it's gonna be, you're gonna have a different tangent line, and that will be a partial f, the slope of this tangent line here, this one here, that will be the partial f, partial y at the point. Now we can take a different direction. Instead of the direction 1, 0 or the direction 0, 1, you can take, let's say, the direction I don't know, let's take the direction 1, 1 here. And you can do the same. You can just, take the image of this line here, the direction vector 1, 1, passing through this point, of course, 1, 1. So it will be this line here, and this curve here. And of course, you're gonna have a different, tangent line. So here's the tangent line to this curve, and we're gonna have a this the tangent line has a different slope, right? So that's the directional derivative actually. So the directional derivative, derivative of f x, y at the point x0, y0 in the direction, let's say, of the unit vector u equal to the so u is the vector ab, is given by, so here's the notation, so directional derivative of f in the direction of the vector u at the point x0, y0. So it's equal to the limit h goes to 0 of f of x0 plus now u. So you vary x and y in the direction of the vector AB, so x0 plus AH minus, x0 plus AH, y0 plus BH minus f of x0, y0 over h. And you can see here in the definition, guys, if the vector u is equal to 1, 0, so if, for example, u is equal to the vector 1, 0, then the directional derivative of f in the direction of the vector 1, 0 at the point x0, y0, that will be limit h goes to 0, so you replace a by 1 and b. So here a is 1 and b here is 0. So that's x0 plus h. So that's f of x0 plus h y0 minus f of x0 y0 over h. And that's exactly the partial f, partial x, right? This is exactly partial f, partial x at the point x0, y0. Okay, and the same, if vector u is the vector 0, 1, then this directional derivative in the direction of the vector 0, 1 at the point x0, y0, that will be partial f, partial y at the point x0, y0. Okay. So let's just do an example. So here's an example. So we have, of course, the limit, the limit definition of the directional derivative, but we're gonna see later there is an easier formula to compute the directional derivative. But first, let's just practice the limit definition. So let's say you have function f equal to x squared y cubed minus y to the 4. And u is a unit vector. So let's say u is a 3 over 5, the vector 3 over 5, 4 over 5. Okay, so of course here the length, u is a unit length. So u is a unit vector. So the length of u is equal to 1. Okay, so let's do this. So what will be the directional derivative? Let's say the question here, what's the directional derivative of f in direction of direction derivative of f in direction of vector u at the point, let's say 0.11. Okay. So 1, 1, that's my x0, y0 here. So this is here, x0 is 1 and y0 is 1. So this is the directional derivative of f in the direction of u at the point 1, 1. Okay, so let's compute this. So what's in the formula? So here's the general formula, right? Here's my general formula. So a, b, that's the coordinates of the vector u. So my a, b here, this would be a and this would be b, right? And x0, y0, again, that's just the point. So it's x0 is 1, y0 is 1. So let's apply now the formula. So it's limit h goes to 0 of f of x0, which is 1, plus h times a, so h times 3 over 5, that's a, y0, which is 1, plus h times b, that's 4 over 5, minus f of 1, 1, x0, y0 over h. Okay, so now we have to plug 1 plus h 3 over 5, 1 plus h 4 over 5 in f of xy. So this is like my x here. So this is here like my x, and this one here is like my y. Okay, and what will be f of 1, 1? Of course, f of 1, 1 is just 1 squared times 1 cubed minus 1 to the 4. So f of 1, 1 would be just 0. Okay, so that will be equal to the limit h goes to 0, so you replace x by 1 plus 3 over 5 h, so that's 1 plus 3 over 5 h squared times y cubed, so that's 1 plus 4 over 5 h cubed minus y to the 4th, so that's 1 plus 4 over 5 h to the 4th, and then minus f of 1, 1, that's f of, so what's 1 cube times 1 square, 1 square times 1 cube minus 1 to the 4th, so that's 1 minus 1, that's just 0, so minus here, minus 0 over h. Okay, so let's compute this. Well, let's factor out here, 1 plus 4 over 5h, so that's limit h goes to 0, 1 plus 4 over 5h. We can factor out 1 plus 4 over 5h cubed. Okay, times, so that's 1 plus 3 over 5h squared minus, so here it's to the 4th, 1 plus 4 over 5h to the 4th, so that's just 1 plus 3 over 5 here, h, 4 over 5, h, and the whole thing divided by h. Okay, so that's limit h goes to 0, so 1 plus 4 over 5 h cubed. So here we can expand this to square, so it's 1 plus 6 over 5 h plus 925 h squared minus 1 minus 4 over 5 h the whole thing over h. So here you can see you can cancel out 1 minus 1, it's just 0. Right, this is 6 over 5h minus 4 over 5h, that will be 2 over 5h. Okay, so that's limit h goes to 0. So we have 1 plus 4 over 5h cubed. So 6 over 5h minus 4 over 5h, that's 2 over 5h plus 9 over 25h squared, and the whole thing divided by h. But here you can see, guys, you can factor out, here you can factor out h. So that's limit h goes to 0. So 1 plus 4 over 5h cubed, factor out h, so that's 2 over 5 plus 9 over 25h over h. So of course h cancel out here, and then we can just replace h by 0. So this limit here, h goes to 0. So 1 plus 4 over 5h cubed times 2 over 5 plus 9 over 25h. H goes to 0. So this is 0, and here this is 0. So it's just 1 times 2 over 5. So when I say 0, so this thing here is 0. This is 0. So it's 1 times 2 over 5. So that will be equal to 2 over 5. So the directional derivative in the direction of the vector 2 over 5, 3 over 5, 4 over 5 is equal to 2 over 5. Okay, again, so you see, guys, with the limit, it can be, the computations can be tricky. So there's a formula. So instead of using limit definition, we can use the following formula. So the directional derivative, actually, of the function f in the direction of the vector u is equal to the vector u dot product. So here, this is the dot product. Dot product with the gradient of f. So here's gradient of f. So this letter here, this triangle here, so it's called nabla. So this thing here is called the gradient of f. So this is gradient of f. And what's gradient of f? So let's say gradient f, let's say a function of xy here. So gradient of f, so this nabla f is the vector partial f, partial x, partial f, partial y. That's the gradient vector. Okay, so this is the gradient of f, or the gradient vector. Again, this is called, so this letter here, this is nabla. This is called nabla. It's a Greek letter. Okay, it's nabla. So nabla f here, or gradient of f, is partial f, partial x. It's the vector partial f, partial x, partial f, partial y. Okay. So let's so example here. Let's apply this formula, and let's use the same example. So we have this example with, my function f, x, y. We said it's x squared y cubed minus y to the fourth, right? And we have the vector u, which is 3 over 5, 4 over 5. And you have the point. So when I compute this directional derivative here at the point 1, 1, right? So let's just apply the formula first. So we said it's u dot product with gradient of f. So what's gradient of f? We said it's partial f. So u partial f here, partial x, partial f, partial y. Okay, so then this is, so directional derivative of f in the direction of u. So u is 3 over 5, 4 over 5, dot product, partial f, partial x. What's the derivative of f with respect to x? So y would be a constant. So derivative of x squared would be 2x times y cubed, derivative and then derivative of y to the fourth, y is a constant, just 0. So it's just 2x y cubed. And then what's the derivative of f with respect to y? So x now is a constant, so x squared times derivative of y cubed. So that's 3x squared y squared minus, and then derivative of y to the fourth, that's 4y cubed. Okay. Now, at the point one, 1, so we have, so this direction derivative would be equal to 3 over 5, 4 over 5. So at the point 1, 1, it means that x is equal to 1 and y is equal to 1. So here, this is x is equal to 1 and y is equal to 1. So this x here is 1 and this y here is 1. So dot product with, so that will be 2 times 1 cubed. And then the second coordinate, we have 3 times 1 squared minus 4 times 1 cubed. Okay, so what I am saying is directional derivative of f and direction of the vector u at the point 1, 1 is equal to dot product 3 over 5, 4 over 5, dot product with, so 2, 1 times 1 cubed, that's equal to 2. And then 3 minus 4 times 1 cubed, 3 minus 4, it's negative 1. So it's negative 1 here. So negative 1. So this is dot product. So remind you how to do the dot product. So 3 over 5 times the 2. So 3 over 5 times the 2 plus, and then 4 over 5 times the negative 1. That's 4 over 5 times negative 1. So that will be equal to 6 over 5 minus 4 over 5. And you see you get the same answer, 2 over 5. So that will be the direction derivative of f in the direction of the vector u at the point 1, 1. Okay, guys, I guess I'm going to stop here. You can find more examples in the lecture notes, and I will see you next time. Thanks.